Hi, everyone. Okay, so we're starting a new chapter, which is called Decomposition of Graphs. The course is going to take a little bit of a change in direction now, in that we're going to be talking about several different graph algorithms over the next two chapters. So to begin, what is a graph? A graph is specified by a set of vertices, V, and a set of edges between pairs of vertices. We'll often write a graph as G, which is this tuple. It's just a pair, the vertices and its edges. So here's an example of a graph with 5 vertices, and then these are the edges. So what does this look like? Well, let me try and draw it. So I've got 5 vertices. Like this. And then I have the edges, 1, 2, 2, 3, oops, 3, 4, 4, 1, and 4, 5. Okay, and that's a graph. So you'll notice here, I'm writing an edge as a set, right? An edge is a set 1, 2, another edge is the set 2, 3. This is the notation we'll use for an undirected graph. And there's also the notion of a directed edge, where instead we'll write it as an ordered tuple, so U comma V. Right here, when we write it as a set, the set with U and V is the same as the set with V and U. There's no ordering, right? It's just it's a relation between a pair of vertices. Here, it's an edge that points from U to V. And so in this second case, we would draw it something like this. You have a vertex U, you have an edge pointing to V, and that is the edge UV. And so if a graph has all undirected edges, it's called an undirected graph. If it has directed edges, it's called a directed graph. And directed graphs can be used, or directed edges can be used to represent things like one-way roads that travel from U to V, or relations between U and V, like U must happen before V. So now, how do we represent a graph, right? We've said it's these two sets, a set of vertices and a set of edges. But how should we represent it? I'm going to give 2 different representations. They each have their advantages. So let's say that the vertex set is V1 through Vn. And so then when we write the cardinality of V, that's just how many vertices there are, and there's n. One choice for a representation is an adjacency matrix, which is an n by n matrix. And the ijth entry in that matrix is a 1 if there's an edge from Vi to Vj, and it's a 0 otherwise. If the graph is undirected, then if Aij is 1, then Abi also must be 1, because, right, if there's an edge from, if we go up, if there's an edge from 1 to 2 in an undirected graph, then there's also an edge from 2 to 1. So this matrix will actually be symmetric. To store this matrix, you have to store all V squared entries, right? Because it's an n by n matrix. And so it requires order V squared space. The advantage of it is that I can in order one, like in one operation, I can look up whether or not an edge is present, right? If you pick 2 vertices, is there an edge between 2 and 7? I just look at the entry 2, 7. If it's a 1, I say yes. If it's a 0, I say no. The alternative is an adjacency list. And an adjacency list maintains a list of neighbors for every vertex. So there's V different lists in the adjacency list. And the list for a vertex U contains all the vertices V that are connected to it by a single edge. So that can be reached from U by traversing a single edge. So the list for vertex U contains all V that can be reached from U with a single edge. So for an undirected graph, that's all the edges, that's all the vertices that are connected by an edge. For a directed graph, it's all the vertices where there's an edge pointing from U out to V, right? So for a directed graph, it's all vertices V such that UV is an edge. If you think about the size of this, then I have a list for each vertex. So I have V different lists. And then combined across all the lists, it just has every edge in it. So the total size for this representation is big O V plus E. Now, note, right, the number of edges in a graph is less than or equal to n squared, or maybe to write it in the way we've been writing it, less than or equal to V squared. So this is big O V squared. If there are a lot of edges that are missing in the graph, like for example, in this graph, right, there's many more than just these 5 edges that would be possible, then this would require less space to store as an adjacency list than as an adjacency matrix. The disadvantage of an adjacency list is that now if I want to know, like, does the edge 2, 7 exist, I have to go to the list for vertex 2 and then scan along that list to see if there's a 7 in it. And so now the lookup time to find out whether or not there's an edge in the graph scales with the number of neighbors of a vertex rather than just being a constant time operation. But in many graph algorithms, instead, what we want to do is find all the neighbors of a vertex. And then the adjacency list is actually the perfect representation for that because it just lists all the neighbors. So let me write out an example, and then we can, of these 2 representations, and then we can talk more about these. So let's say I have this graph with V4, V1, V3, V2. And let's say it's a directed graph. So it has a directed edge going from 1 to 4 and 4 to 1. There's an edge from 2 to 1, from 2 to 3, and from 3 to 4. So as an adjacency matrix, I create this matrix A, which should have looks like this. And let's label the rows in the column. So V1, V2, V3, V4, V1, V2, V3, V4. So the ijth entry is a 1 if there's an edge from I to j. So 1 has an edge going to 4. Oh, I missed 1 edge from what I've drawn in the notes. And there was an edge there too. So here, 1 does not have an edge to itself. It doesn't have a self loop. It doesn't have an edge 2 pointing towards 2. It has an edge pointing towards 3, and it has an edge pointing towards 4. For V2, it has edges just to 1 and 3. So 1, 0, 1, 0. For V3, it has an edge going to 4. And 4 has an edge going to 1. As an adjacency list, it would look something like this. So you could think of it in Python, you might do a list of length 4, where each entry in that list is a list itself. So you'd have the list for V1, for V2, for V3, for V4. V1 just lists the 2, something like this, V3, V4, in any order. V1, V3, V4, and V1. And so one thing I want to say, right? Like, let's say I want to design an algorithm, which actually coming up, we're going to do exactly this, where I want to loop over the neighbors of a vertex. So let's say I want to loop over the neighbors of V1. Then the adjacency list is the best representation, because you can see I just loop over this list here, V3, V4. And so that for loop only has to inspect the neighbors itself. If instead I want to do it with the adjacency matrix, I have to loop over the entire row. So it's always going to be big O of V for each for loop iteration, because I'm going to go 0, okay, no edge, 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 right? So this is kind of just extracted the non-zero entries. The disadvantage, as I said, is that if I want to figure out is there an edge from 2 to 4, here I can look it up right away. In this one, I have to loop through this list and see that there's no V4 in there. Okay, so now let's start with our first algorithm. We're going to go through some basic algorithms. I'm sure you've seen them before, but hopefully, it's just getting us all up to speed on graph algorithms. And the first one is going to be depth first search. So the question we're going to think of is, what parts of a graph can we reach from a given vertex? This is kind of an interesting thing with graphs in that, of course, when I look at a graph, like when I've drawn it on paper, it's very easy to see these types of things, like what parts of this graph can be reached from vertex 1? Well, it's everything, right? I can travel along these edges and get to any other vertex. But if instead I'm given an input that looks like this or like this, you can see that there's some work to be done to figure out what can be reached from V1 in this case, or what can be reached from V1 in this case. And so that's exactly what depth first search does. And the idea is we're going to be given the graph as an adjacency list. It'll be more efficient to do that. Start at some vertex and explore all its neighbors, and then recurse. So add those neighbors to something that I can then repeatedly now explore its neighbors. So to begin, we initialize a Boolean variable for each vertex called visited, and we set visited to false. Right? None of the vertices have been visited. And then the procedure is going to be called explore. It takes in a graph as an adjacency list, and it takes in a start vertex. And what it will output is it'll set visited U to true for all vertices U that can be reached from V by traversing edges. So we start by setting the input vertex to true, and then we loop over all the edges, leaving V. All the edges, they go to a new vertex U. And if we haven't yet visited that U, then we call explore on that U. So this is a recursive implementation again. And now let's think about what happens here. Why is this algorithm correct? Does it actually find all the vertices connected to a given that can be reached from V? So the way we're going to prove this is, let's suppose it's not correct. So this is called a proof by contradiction. So suppose by way of contradiction, there is a path from V to some U, but visited U stays false at the end of the algorithm. So there's a path, right? So let me just draw that path. It starts off with V, then it goes to some other vertex. I don't really know what happens. And let's say then it goes to some vertex Z, then it goes to some vertex W, and then it goes along more, and it finally gets to U somehow. So this is a path that's in the graph from V to U. Okay, and let's say that Z, if it never set U to false, maybe U was the first one that it didn't set to false, like the vertex immediately before U on this path was set to true. But let's say in general, the last one it set to true was Z. So let Z be the last vertex on path set to true. And so then the next vertex on the path is W, right? And W would have to be false. Then, so W is next vertex on path. And visited W equals false. W could be U, right? It's either U or it's the vertex before U on the path. But in any case, since Z was set to true, or visited Z was set to true, we know that explore, the only way that something gets set to, the only way, a vertex gets set to true is if explore has been called on it, right? This visited V equals true happens within the call explore GV. So we know that explore GZ had to be called. So, but since explore GZ was called and ZW is an edge, we know we loop over all the edges in line 2, it must be that explorer GW was called. Which implies that visited of, if explorer GW was called, then visited of W has to be set to true. And that's a contradiction, right? Because we had visited W is false and visited W is true. So that's a contradiction. So we assumed something, right? We're trying to prove that this first thing doesn't happen. We're trying to prove that, there can't be a vertex that's connected by a path that didn't get found by the algorithm. So we assume we take the opposite stance. We assume it happened. And then what we do is by assuming it happened, we arrive at a logical contradiction. So we assumed it happened. If it happened, that meant there had to be a vertex that was set to false, but then we logically follow that through and we get that vertex must have been set to true, and that contradicts itself. And so the original premise that there was a vertex that didn't get discovered has to be incorrect. And so that's the end of the proof. That's the way we do a proof by contradiction. You can also prove this by induction, if you like, where we would use an inductive hypothesis that looks something like, for any k greater than or equal to 0, all vertices within k hops from V get visited. And so then hopping across k edges. And so we start with the base case where we go 0 edges. We know that V is visited, so that's true. And then we assume it's true for k minus 1, and we prove it's true for k. That would also work. Now, let's take this graph here. See if I can steal it. Copy and put it down here. Okay, and let's say we call explore G on V2. Then what happens? I'm going to use a highlighter here. So V2 is going to, when we call explore on V2, V2 gets set to true and it explores all the outgoing edges, right? So let's say that first it explores the edge V1. Then when explore V1 gets called, it then explores the outgoing neighbors of V1. It'll probably do it, let's say it does it in order from lowest numbered vertex to highest. So it'll go along here next and explore V3. Then explore V3 gets called and it goes across to here. It calls explore on V4. V4 has no unvisited neighbors. So that explore call ends. It goes back up into the explore V3 call. This one has no unvisited neighbors, right? The only neighbor is V4, which already was visited. So it goes back up into the explore V1 call. Again, this has no unvisited neighbors, so it goes back up into the V2 call. This now has no unvisited neighbors because V3 has been visited, and it terminates. And so you can see we kind of traversed this path in kind of a depth. That's why it's called depth first, because we kept going deeper and deeper into the graph through these, we call recursively, and then we immediately, once we find V1, we immediately explore V1 rather than exploring all the neighbors of V2 first. So depth first, this algorithm that I presented so far is called explore. It's not yet called DFS. Depth first search is just going to take in a graph and explore the whole thing. So explore only finds a portion of the graph that's reachable from V. In general, like if a graph is not connected, explore will only find a portion of it. So like, let's take an example that looks like this, where I have, let's say V4 is here, V5, V3, V1, V2, and it has some edges. Then if I call explore, this is an undirected graph that I'm drawing now, G on V1. It's going to, again, it'll go find a neighbor, call explore on that neighbor. Oops. Find that neighbor, and then finish, and it'll just terminate, right? It found all the vertices that are reachable from V1. So, and you notice, right, it didn't find V4 or V5. And so DFS, all it does is it runs explore in each component of the graph. And so DFS then is just kind of a wrapper for explore. It starts off by initializing all the visited variables to false. You see it takes in a graph, but it doesn't take in a start vertex. So that's that's by convention. And then it starts, basically, it takes a for loop over the vertices. So basically think it picks the first vertex, I don't know, V1. And if V1 hasn't been visited yet, it calls explore on it. That's then going to set visited to true for 2 and 3. So now in this for loop, it won't do explore on 2 and it won't do it on 3. It'll try 4 now, and then it'll call explore again on V4, which finds V5, and then the for loop is done. So basically, in here, it'll initiate and explore 2 times, one for each of these connected components of the graph. I'm going to say that the correctness of this is correct because basically it calls explore, finds a connected component, then In here, it's exhaustively going through all the vertices. So it checks all the other vertices to find one that hasn't yet been explored. That must be in a new connected component, and then it calls explore on that. So the correctness follows from the correctness of explore. Let's now think about what the runtime of this is. And there's two basic components to the runtime. So first, we have that visited is initialized for each vertex. So which I'll say is big O of V, right? Order one time to set each variable. And now we have to think about what happens in the calls to explore. So we know that to explore the entire graph, the function explore GV must be called on every vertex. So it must be called on all V in the vertex set. And so if we go back up to explore, that means it's going to have to set visited to true for each vertex. And then it's going to have to do this for loop. So first, line 1, it has to do that for every vertex. So the runtime set visited V equal to true for all V is going to be big O of V. And then the other part is the loop over the edges. So let me just write that first, and then this is a part where people often get confused. So let's look at explore quickly. So notice that in a call to explore GV, we loop over all the neighbors of V, right? All the edges, all the vertices U basically that are connected to E by an edge. So if you think, like, let's look at one of our pictures. When I call explore on V1, or well, we did V2 first. When I call explore on V2, it's going to loop over these two edges. When I then call explore on V1, it loops over all the outgoing edges of V1, which is this edge and this edge. V3 is this edge. V4 is this edge. And you can see that combined, I actually just inspect each edge once, right? Because on each explore call, I only look at the edges that leave that vertex. They only get looked at once across the entire execution of depth first search, which is just that one time that I call explore on, let's say, V2. So in this, each edge in a directed graph, UV is explored, or examined, I should say, just once. When explore GV is called, or GU is called, sorry. when explore GU is called. In an undirected graph, let's go up to an undirected graph picture. So now when I call explore on V1, it's going to inspect this edge and this edge. When I call explore on V2, it's going to inspect this edge and this edge. You can see this green one now has been inspected twice, once from the V1 end and once from the V2 end, but it won't get inspected any more times. Then I call V3, it's going to inspect this edge, which is the second time for it, and this one, which is the second time for it. And then I call on V4, it's going to inspect this. And finally, I call on V5, it's going to inspect it from the other end. And so in an undirected graph, each edge gets inspected twice, once from the U end and once from the V end, since it's an undirected graph. So for an undirected graph, each edge UV is examined twice. Therefore, in the whole DFX execution, the combined time spent looping over edges is big O of E, right? It's either once for each edge or twice for each edge, if it's directed or undirected. And so you can see if I look at all my runtimes, I have big OV for initialization, big OV for setting visited to true, and then big O of E for the loop over the combined loop over the edges. And so the runtime of DFS is big O V plus E. And that's assuming the graph is given as an adjacency list. And if you think the adjacency list took up big O V plus E space, so even just to read that input in takes big O V plus E time, which means that the algorithm is running linear in the input size, which is about as good as you can hope for to explore the entire graph. So note, this is linear in the input size. So the one thing I just want to emphasize is many people, when you look at this loop, you think, okay, it's looping over all the edges. That's big O V. And now it's doing it for every vertex. So it's big O V squared. But that's not true, right? Because it's not looping over every single edge here. It's only looping over the edges that leave V. Right? And so that's the kind of key thing. So people make a mistake in two ways. One is that they might say, each time you execute two, you loop over all edges in the entire graph. And then you end up getting this runtime that says V times E, which is wrong. Or the other one is that you think that this for loop takes big O V each time, which again is not true. And then you would get V squared. And so neither of these are the correct runtime. I'm just trying to highlight two potential issues that people have in characterizing the runtime of algorithms like this. The correct runtime is following this logic, and we get the runtime of big O V plus E. Okay, so in the next lecture, we'll start going over breadth first search. And also, I think first we're going to use, before we go to breadth first search, we're going to use depth first search to do some things, to explore the graph and determine some of its properties, like whether it has a cycle and how many connected components it has. So thanks, everyone. I'll see you in the next lecture.